Hello, good afternoon, good evening to everyone watching. Welcome to another live session at the Reactors. Before we get into the session, please take a moment to read our code of conduct. We're all here to learn, so please be respectful of other people's views, understanding of differences, and please be kind and considerate in the way you engage. The chat will be open throughout, and we do encourage you all to participate. Today, we are back with episode 2 of Introduction to R. And this episode will again be led by Carlotta and Eric, who will talk to you all about Introduction to Regression Models by using R and Tidymodels. So with that, I'm now going to bring Eric and Carlotta up to the screen. Hi, Carlotta. Hi, Eric.
Hello, hi everyone.
Hello, hey everyone.
So the stage is all yours. I'll be in the background if you need me. Just shout my name. Over to you now.
Great. Thank you so much for the great introduction, Rav. And thank you all for joining us for this session today, which is, as Rav just said, the second workshop of a series designed for getting started with R for data science. So if you missed the last episode, you can also go back after this workshop and rewatch it. It was on exploratory data analysis with R, while today we'll be dealing with introduction to regression models by using R and the Tidymodels framework. I'm Carlotta Castelluccio, Cloud Advocate at Microsoft, focused on AI and machine learning technologies and their use in education. And today I'm thrilled to be here with Eric. Hi, Eric. How are you? Do you mind introduce yourself?
Hello, Carlotta. Yeah, again, my name is Eric Kwanjao. I am also really happy to be here again. You know, talking about R and Tidy models, now having the Microsoft Learn path up and running. So yeah, really excited to explore this series with you and learn from each other. And yeah, excited. So what do you have today, Carlotta?
Thanks, Eric. So, yeah, as Eric just mentioned, I would like to remember that you can follow us along with this module um, uh, using this link. And what we have today, we have a great learning agenda. So we will be dealing with what is regression, of course, and also in which type of scenarios you should choose to use a regression model. We will talk about training and evaluating a regression model. And finally, we will present different kind of regression models. And we are going also to do some practical experimentation through an hands-on workshop because we want to put into practice the theoretical skills we will be gaining with this workshop and also with the Learn module. So let's start with an introduction of regression. Regression is a statistical technique that uses models to predict a number, a quantifiable value. This value can be, for example, a price, an amount, a size, or another scalar number. Regression models provide an excellent foundation to understanding how more complex machine learning techniques work. And the real world situation, particularly when little data are available, regression models are very useful for making predictions. For example, if a company that rents bicycles wants to predict the expected number of rentals on a given day in the future, a regression model can predict this number. A model could be created using existing data such as the number of bicycles that were rented on days where the season, the day of the week, and so on were also recorded. So regression works by establishing a relationship between variables in the data that represent characteristics of the things being observed, known as features, and the variable we're trying to predict, which is known as the label. Recalling our company that rents bicycle and wants to predict the expected number of rentals in a given day, in this case, features include things like the day of the week, the month, and so on, while the label is the number of bicycle rentals. So now I will let Eric tell you more about how to train and evaluate a regression model.
All right. Perfect, Carlotta. Thanks for that great introduction about what regression is. So it's worth noting that regression is a form of supervised learning, which is a learning task of getting a function that maps an input to an output based on input-output pairs. So in supervised learning, it's very common to split the data into two subsets: a train set and a test set. So the train set is the typically larger set, which is used to train the model. And this typically means applying an algorithm that determines a function encapsulating the relationship between the features and the label. And the test set, on the other hand, is the smaller holdback set, which is used to evaluate the model by using it to generate predictions for the labels that he has not seen before and comparing it to the actual known labels. So this helps us, the test set helps us to evaluate how well the model will perform on data that it has never seen and give us a rough estimate of its performance out there in the wild. So yes, Carlotta, this is how every regression model fitting starts by typically splitting the data into a train set and a test set. So yeah, that's it. Take it away, Carlotta.
Awesome. So uh, now I would like to take a simple example to show in practice how we can train and evaluating a regression model to predict a numeric quantifiable value. So I will use the scenario, which is the same introduced in the first slide. So a company renting bicycles that wants to predict the future number of rents. So for sake of simplicity, we are going to consider only one feature, which is the average temperature of the day. And so the dataset that you see displayed here in the deck has two columns: the feature X, which is the average temperature, and the label Y, which is the known label. Then now we will start by splitting the dataset into two subsets, as Eric just explained: a bigger one, which is the training dataset to train the model, and a smaller one called the test dataset, which is used to evaluate the model. Remind that training the model means finding the mathematical equation we saw earlier to calculate the number of rentals given the temperature feature. So the function f, for which f of x is equal to y. Let's start now by plotting the training values for x and y on a chart. In this simple example, the plotted points form an almost straight diagonal line. In other words, there's an apparent linear relationship between x and y. So we need to find a linear function that's the best fit for the data sample. There are, of course, various algorithms we can use to determine this function, which will ultimately find a straight line with minimal overall variance from the plotted points, like this one. So the line represents a linear function that can be used with any value of x to apply the slope of the line and its intercept to calculate y. So now that we've defined our predictive function, we can use it to predict labels for the validation data we have back. So this test dataset, and compare the predicted values, which we typically indicate with the symbol y or y hat, with the actual known y values. So the following graph shows in red the position of the predicted points for the temperature values of the test dataset, along with the position of the data points in blue, plotted by using the known labels of the test dataset. So the values you can see below in the extra column represent the predicted values for the number of rentals given the three temperature features in the test dataset. At this point, you can measure the variance between the predicted and actual values in various ways in order to evaluate how well the model performs. One of the most common ways to measure the loss is to square the individual residuals, sum the squares, and calculate the mean. So squaring the residuals has the effect of basing the calculation on absolute values, ignoring whether the difference is negative or positive, and giving more weight to larger differences. So this metric is called the mean square error, and from the mean squared error, it's also possible to compute the root mean square error, whose advantage is that the loss is expressed in the same unit of measurement as the predicted label value. So for this example, you can affirm that on average, incorrect predictions are wrong by around 3 rentals. So with this simple example, we just explored how to build a linear regression model, which is one of the easiest regression model we have. But for wider dataset and more complex problem, we need to experiment with different kind of algorithms. And I let you, Eric, tell us more about this.
All right, Carlotta. Yes. So let's talk about experimenting with models, right? So as Carlotta said, typically in any real world situation, we'd want to experiment with multiple models because one, our data may be too complex for a simple model to handle, or second, we may not know the exact model that will fit the data well. So it's worth experimenting with a one model or two. So let's start with the linear regression model that Carlotta has gracefully explained. So the linear regression is one of the simplest algorithms for doing supervised learning, for doing supervised regression learning, that is, and fits a straight line or surface that minimizes the discrepancies between the predicted and the actual output values. Though it may seem somewhat dull to more modern statistical learning, it's still very useful and widely applied statistical learning approach, and it serves as a really good point for more advanced approaches like the tree-based algorithms. So tree-based algorithms are a class of non-parametric algorithms that work by partitioning the feature space into a number of smaller regions with similar responses using a set of splitting rules. So this means that the input variables or the features are repeatedly segmented or divided into subsets using if-then rules to build a decision tree, and then each branch of the tree is tested for prediction and accuracy, and for efficiency and how it would perform on new data that it has not seen. So examples of tree-based models are such as a decision tree or bugging trees that combines many decision trees. So another model worth experimenting with is ensemble algorithms. So ensemble models are these models that combine multiple base models in a clever way to achieve better accuracy than a single model. So for instance, a good example of ensemble algorithm what you may have heard of is random forest algorithm that combine many base decision trees and then does an average. Or another algorithm is such as a boosted trees that combines many base decision trees and then builds each on top of each other that the subsequent tree reduces the error of the previous one. So this is all ensemble algorithms are all about, combining multiple base trees in order to improve the accuracy or the metrics of a single base model. So these are some of the things that you'd want to do in real life to experiment with multiple models to improve performance. Another thing that you could do is play around with model hyperparameters. So you may find that simple models with small data sets can be often fit in a single step, but larger data sets which require more complex model to fit, it will be better to fit repeatedly using a simulated data set and then check for model performance and see whether you are getting a better fit of your data. So the parameters that let you control that model training on simulated data is what are known as hyperparameters. So for example, in neural networks, a hyperparameter could be the number of hidden layers, or let's say in a random forest, the hyperparameter could be the number of trees that you would want to be in an ensemble algorithm. So model performance depends, for complex models, depends heavily on these model hyperparameters, and finding the best hyperparameters can really improve model performance. So and this is what is known as hyperparameter tuning, and the process of finding the configuration of hyperparameters that result in the best performance. So we'll see this. This is clearly illustrated in the learning path, where we fit multiple models and tune multiple hyperparameters. And we just saw it worth mentioning before you get into the into the learning path itself. So anyhow, these are the ways that you could approach a real life modeling approach by trying out multiple models, and in some instances improving models using hyperparameters. So yeah, Carlotta, that's it from me. So what are we going to be doing today with this information?
Yeah, great, Eric. Thanks. So I think it's now time to put into practice some of these theoretical skills and concepts we just dealt with. So let's imagine for this challenge today that we are a real estate agent, and we've just been handed a couple of new houses at different locations of the city. We don't know the selling price of these houses, and we want to get an estimate of it by comparing it with that of other houses in the location for which we know the price. So in this challenge, we'll use a dataset of real estate sales transactions to predict the price per unit of a property based on features such as the property age, the availability of local amenities, and the location. So, Eric, it's time to take the challenge. Can you show us how we can access the ready to go environment needed to go through this challenge on Microsoft Learn?
Sure, Carlotta. Yes, with very much pleasure. Yeah. So welcome to again introduction to regression models by using R. So what we'll be doing is we have a ready environment for you in the Microsoft Learn R path, create machine learning models with R and Tidymodels. So what will be when you click on the link in the that is provided, you we go to this learning path, and we're interested in the models, introduction to regression models in R and Tidymodels, right? So at the end of each module, we have a challenge. So this is a notebook that has some pros and some code and some blank spaces that you'll be going to be filling along the way, and you just need to log in with your either GitHub or Microsoft Learn email, and yes, you are ready to access the sandbox. So hope my screen is visible for now.
Yes.
Yes, perfect. So to activate the sandbox, you would require to be logged in, and once you click the activate sandbox, you get a ready sandbox, has all the modules, all the data, and you just have to come in and start writing code. So yes, that's how you would code along with us, which we invite you to do. And yes, let's have fun together. So yes, Carlotta, do we get started now? Are you ready for this?
Sure, ready. Let's
Perfect,
go.
perfect. All right. So again, just a reminder, doing regression. And so in this challenge, we are dealing with a notebook where we'll be predicting the selling price of a residential property depending on factors such as the age, ability of local amenities, location, and other factors. So this is a Jupyter notebook on Microsoft Learn that has chunks of code, interactive notebook where you can add chunks of code, you can edit, according to how you see fit, and you can run. And yes, allows you to combine prose and code together, and really makes it a shareable shareable and reproducible notebook for you in the future, where you can come back and start off where you left off. So yeah, let's begin with every machine learning task by loading in the required packages. So we're loading in the tidyverse and Tidymodels packages. So in last time we discussed what the tidyverse is, a collection of packages that allow you to do visualization, wrangling data, communicating. So it's a set of packages for making data science easy and fun. And Tidymodels is a framework for doing machine learning and modeling in R. So once you have this loaded, you also reading the data. It's a CSV file, so we'll use the read CSV command to load in the data. And yes, we will be, after we will have loaded in the data, we'll check the first 10 rows of the data to get a glimpse of what the data looks like. So as this is running, let's see what that looks like. So yeah, Carlotta, as this is running, any package you remember in the Tidyverse that you liked?
Here we are. So we have the data set
Perfect.
ready.
Yes, here we go. Keep that thought. Yeah. So Carlotta, what are we dealing with today in terms of data?
As you just mentioned, Eric, so the primary task of a data scientist is explore data, right? So let's go ahead and see how it looks like our data set. So this data set contains 7 columns. The first column provides the information about the date of the sale transaction. Then we have the age of the building, the distance to the nearest rail station in meters, the number of convenience stores within walking distance, the geographic coordinates of the house, like latitude and longitude, and the price per unit, where the unit is 3.3 square meters, which is the value we want our model to learn to predict. So this workshop, as you just mentioned, is structured in 8 questions that will guide us from exploring and preparing the data, identifying predictive features that will help predict the price per unit label, and train a regression model that achieves the lowest root mean square error. So for each question, we have a few lines of codes to complete by filling out blank spaces. And feel free to interact with us, maybe try to guess some answer, or just ask any doubts of curiosity you might have while we go through this challenge. But first of all, let's start our analysis of the data by examining a few key descriptive statistics by leveraging on the summary tools desk function. Eric has just run this piece of code, which show us the most common summary statistics for this data set. And they are the mean value, the standard deviation, which is the measure of how much the observation values differ from the mean, the minimum value, the maximum value, and the quantile values. So the quantile values are the threshold values for 25%, 50%, which is also the median, and 75% of the data. And from these, we can see that the mean number of price per unit is around 38. And there's also a comparatively small standard deviation, indicating not much variance in the prices per unit. But we might get a clearer idea of the distribution of price values by visualizing the data. Right, Eric? So do you mind maybe to guide us through data visualization for the price per unit label?
Sure, Carlotta. Yeah. So, as they always say, the simple graph has brought very much information to the data analyst mind than any other device. So let's see how this will help us improve our understanding of the data. So we load a library called Patchwork. So Patchwork allows you to combine multiple plots in a single plane. And so this is just briefly go through this. So here we start by setting the theme of the plot. So we want a light theme, so that means we remove a gray background. The background will be white. So and then we start by passing the data, which is our estate data, to ggplot. So ggplot, elegant package for doing data visualization in R, which we covered last time. So we after you pass data, we need to tell ggplot, why do I spot why do I plot where each aesthetic. So we want to plot the price per unit to the want to plot price per unit to the X aesthetic. So that is it, and then we tell ggplot what type of plot you want to to graph and want a geom histogram. So because we're a histogram, we specify the beans and what color will fill the beans, and we chose midnight blue. And this other is just adding vertical lines for statistics such as the mean, the median, and the mean and the median. And the rest is specifying X labels and Y labels, how we're going to label the X and Y aesthetics. Again, we want to plot a box plot. So again, we start with the data, and then we tell ggplot map price per unit to the X aesthetic and one to the Y, and then fill, because we want a box plot, to specify it using geom box plot, and the color we want to fill it in. And then we use patchwork to combine a histogram and a box plot on top of each other. So once we run this, we are able to get a histogram on top of a box plot. And so this shows how the price distribution is. As you can see, we have an almost normal distribution. And in statistical terminology, this means that most of our data resides at the middle. So as can be illustrated by the summary statistics and by also these beans having high match frequency that are closer to the summary statistics. So have a lot of the data being located near the middle, the mean, the middle distributions of our data. We can also see from the box plot, which is a planar view of the histogram, that we have some bit of outliers. So I think that's somewhere we can start. We can start with dealing with some of these outliers. So Carlotta, will you be kind enough to remind us what outliers are and how do you deal with them?
Of course. So an outlier is a data point that significantly differs from the other observations in the data set. So the easiest way to spot outliers is what we just did, right? So to graph the distribution of the data, and to spot outliers. In this case, we spotted outliers for a price per unit greater than 70. So that's why the first question asks us to start from our data set called isDate_data and filter in order to create a subset that contains observations where price per unit is less than 70, less than this value. I think we start with an easy one, right? So it's quite straightforward, this question. We have almost the answer in the question, because we have the suggestion of using the filter verb, and also we have some suggestions about which parameters we should put into give as input for filter. So Eric, can you maybe recall us what filter does in R and go through this first question?
Yes, Carlotta, that's a really keen observation, that most of the answers we found in the question itself. So here we are asked to filter to create a subset that contains observation that meet a particular condition. And in R, filter, we use the deployer package, which has the filter verb. So what filter allows you to do, filter allows you to keep rows that satisfy your conditions. So for instance, here, you want to keep rows where the price per unit, you want to keep rows in the data set where the price per unit is less than 70. So yes, filter will be the most appropriate verb to create a subset that meets our conditions. So yes, please feel free to code along with us or to put your answer in the chat or ask a question. So let's deal with this first question. So starting with the estate data. So for those who are not familiar with R, this is known as the pipe operator, allows you to pipe a data set on the left to a function, to a function on the right. So as we'll see, so we want to start with the estate data. So the pipe can be read as and then. So we want to, starting with the estate data, and then we want to filter for what condition. We want filter for rows for the price per unit is what is less than 70 because we saw outliers, we have outliers for values greater than 70. So that is how we would solve this question. And if you want to see the resultant, subset, which is safe to estate data, you can just run it by just writing the variable name where we have saved that operation. And yeah, so this represents the data where the price per unit is less than 70. So yeah, so that's how we do it. In this line path, we have an auto-grade solution known as OTAR attached to it. So here you can run this code chunk to check whether your answers are correct and can provide you some feedback on how it may have gone wrong, or in this case, where we have successfully done the question well. So yes, so that's how we would filter for rows that satisfy our condition in the process remove outliers. Now that to have outliers removed, we can rerun the plot to see observations, how they look like, and we can get a clearer view of a good data set that is not that has almost bell-shaped, almost bell-shaped, so very not skewed to the right or to the left. So this perfect data set to start doing our modeling. So yeah, so that said, Carlotta, time to view numerical relations, right? So what is this? What are numerical relations, Carlotta, if I may ask?
Yeah, so it's time to explore the relationships between our label, so the label we want to predict, and the other features in order to explore which one are the most predictive ones, right? And we'll start by exploring numerical correlation. So this is a statistic, a statistic value between -1 and 1, which indicates the strength of a linear relationship between the features and the label we want to be able to predict. So for numeric feature and label columns, we can create a scatter plot that show the intersection of the feature and the label values. And that's exactly what we want to achieve by answering to question 2, which is our next question. In particular, question 2 asks us to pipe 3 different actions. So the first action is to pivot longer the data to create 2 new columns called features and values, then group by features, and add a new column to collect the result of computing the correlation between values and price per unit using the core function. So pivot longer, group by, and then calculate the correlation. So Eric, since I see a new verb here, I see pivot longer. Maybe you can introduce it to us, right?
Yes, Escala. Yeah. That's very key observation there. So we have pivot longer. So what pivot longer allows you to do, allows you to kind of reduce the number of the columns in the data set. So for instance, if we have a data set that has a lot of columns, want to pivot it longer, we would want to reduce the number of columns so that the data set can have instead more rows than more columns. So this is typically used because in R, because we want to simplify data visualization, as you'll see, by leveraging on some features of ggplot. So we're able to plot, using one piece of code, we're able to plot multiple plots instead of using loops to do that. So yeah, so that's what pivot longer does, as we'll illustrate in just a second. So yeah, so let's get down to this code chunk that helps us explore the relationship between the predictors and the outcome, before fitting a model, because it's an important step. So yes, Carla, so let's start with the first question, which is pivot longer the data, right? So yeah, so here we start by filling in here. So we start with the estate data, and then we pivot longer. increase the number of rows and decrease the number of columns, whereby we want to pivot longer all the columns except the price per unit to a new column under the name features, and the values under the new column known as values. So let's, for visualization, let's see how the data looked like before we pivot longer. So let's say estate data, and then let's copy this here. Let's look at the first 10 rows. N is equals to 10. Okay, so this will be really helpful in helping understand what we want to do. Well, let's reduce this. 3 is better. 3 is a good number. So yes, so want to pivot longer the data. So whereby all these rows, all these columns, except the price per unit. So this means you want to pivot longer all the columns except the price per unit. Go to a new column known as features. So the names of these other columns will go to a new column known as features, and the corresponding values will go to a new column known as values. So again, we can see the result of this just step by step. Just let me just paste that here. You can see how we transform this data to a longer set. So we see how we transform this data to a longer format where all the columns except the price per unit go under a new column known as features, and their corresponding values go under a new column known as values. So Carlotta, is that the first part of it, right? So the second part, what does it what does it want us to do?
Right. So for the second part, we need to group by the new column we just created. So the features column. Yeah, that's it.
Perfect.
As easy
All right.
as it.
Yes, as easy as it is. So what we want to do now is we want to group by the features. So remember from last time, group by, we use the group by verb. So the group by verb allows you to make subsequent calculations based on unique values in a given column. So for instance, here we are grouping by features. We are grouping by these new variables, these new observations we created, so that means for each unique feature, such as transaction date, a given a subsequent calculation will be performed uniquely based on the value of each distinct feature. So yeah, so as easy as that, we have grouped by features. And then what do we want to do next? And then for each feature, we want to calculate the correlation coefficient between the values and price per unit. So here we have the mutate verb. So what does mutate allow us to do? So mutate allows you to do either two things: to either modify the existing column, or in our case, we want to create a new column known as core coefficient, which is the correlation between the values of each feature and the price per unit. Price per unit. So yeah, so that's how would calculate would create a new column known as correlation coefficient, known as core coef, that calculates the correlation between the values and the price per unit. So again, we can run this just for a sanity check and see what we get. So if we run that, we can be able to see we started here, and then we've created a new, we pivot longer the data, and then we create a new column known as core coefficient, which is the correlation between each individual feature and the corresponding values. So yeah, Carlotta, I think we've answered most of the questions there. So the subsequent operations just are we once again use mutate to modify the features column, whereby we use the function paste. So paste allows you to combine two strings together. So we want to combine the feature string and the correlation coefficient that we've just calculated. Once we combine that to a single string, we want to ungroup, because group by it's a good practice to ungroup once you've done a group by. So this gives us this new table where we have these newly created values, and as you can see, we have combined the features and the corresponding correlation coefficient. So yeah, so that's how we break down this long question into these individual subsections using the pipe. As you can see, allows us to really string a lot of calculations at each step and do new ones depending on the previous value. And again, you can check whether your answer is correct. And yes, our answer is correct. And we have a pivoted table, and I found the correlation between the existing numeric columns and the price per unit. So, Carlotta, now that we have that, time to do some plotting again, right?
Right. So we can plot some scatter plots in this case to see visually if how this numerical correlation works between the label and our features.
Perfect, Carlotta. Yes. So let's see why it was worth doing the pivoting longer the data. So now that we have the pivot, we have pivoted the longer the data. Once again, we pass it on to ggplot, and then tell ggplot map the values to the x aesthetic and the price by unit to the y, and then color the color by the features. So we'll color our points or our scatter plots by each distinct feature. And then we tell ggplot want a scatter plot, and a scatter plot in ggplot is represented by geom point. So we add a geom point to the layer, and then we specify the opacity using the alpha alpha verb, and then we say we don't want any legend. And then we will facet wrap. And so what facet wrap allows you to do, allows you to plot a scatter plot for each of the features. So now that we have pivoted longer data, you can plot a scatter plot for each feature here without needing probably loops or something. So that's what facet trap allows you to do. And yes, the last one is just a color aesthetic to it. So now that we have a scatter plot, we can see clearly that some features have a strong positive correlation, and others have not a very strong positive correlation. And yes, so for instance, we can see we can see transit distance with price. We can see that has a negative correlation of negative 0.7. So what that this means is as the price increases, as the transit distance increases, we see there's also a decrease in the price. So the value is represented by the correlation coefficient negative 0.7. For others, such as the latitude, we can see that as the latitude increases, we have houses, the price per unit of houses increasing. So that means we have some geographical effect on based on the price, based on the latitude and the longitude. And yes, some have very low correlation, such as the transaction date and the number of stores. So yes, this gives us a glimpse of what could be predictive, what could not be predictive, and yes, a good way of seeing that was by plotting the correlations. So Carlotta, now that we have this information, we have seen that location clearly affects price. Distance from the public transport, as it increases, the price decreases. That makes sense. So what can we do with this from this point?
Yeah, sure. So as you just said, we notice that transaction date and local convenience stores seem to have low numerical correlation, right?
Yeah.
But we have an additional type of analysis we can do here, because this could just tell us that these are discrete values. So it might work better if we treat these columns as categorical features rather than numerical features. And that's lead us to question 3, because question 3 asks us to build again another piped sequence of actions to perform mainly 3 actions on the data. First of all, only keep the columns we want to analyze more, right? To explore more. So transaction date, local convenience stores, and of course the label, so the price per unit, because we are still analyzing the relationship between the label and the features. Then encode columns, transaction date, and local convenience stores as categorical, so as a factor. And finally, pivot longer again the data to make it easier to visualize the data. So let's begin. Let's maybe break this question down into the 3 actions we need to perform for sake of simplicity. So the first action, let's recall that, is keeping only columns transaction date, local convenience stores, and price per unit. So extract these 3 columns from the dataset. We previously used the filter verb to extract a set of rows from a dataset. But which verb shall we use to extract a set of columns now?
Yes, that's a really good question, Carlotta. Yeah, so we need to keep these 3 columns: the transaction date, the local convenience stores, and the outcome price per unit. So how do we select this? And the answer is in what I've just said. We use the select verb. So in R, the select verb allows you to pick columns that you want to further analyze. So yes, so and that is what we'll be using. So the verb is select, and in select. So what this does, we've taken the estate data, and then we are selecting 3 columns: the transaction date, the other column is the local convenience stores, right? Um, Picking the local convenience stores, and lastly, we are picking the price per unit. Price per unit. All right. So first part done. Yes. So again, easily seen by just running that, and you can see we've narrowed down to these 3 columns. All right, Carlotta. So what are we doing next from now that you have achieved that?
Great. So we extracted our 3 columns. Now the next step will be to encode transaction date and local convenience stores as categorical. So to explore the categorical correlation with the label. And we will use again the verb mutate for that, right? Because we want to convert a column into a factor. Sorry, 2 columns in this case into factor.
Into factors. Yes, Carlotta, very right. So the mutate verb, as we say earlier, allows you to 1, create a new column, or 2, modify an existing column. So here we want to modify the transaction date and the local convenience stores from numeric to categorical, because we saw being them as numeric, they were not really predictive. So how do we do this? So we want to mutate. We'll use another verb called across. So across can be used with mutate to modify multiple columns at once. So we'll mutate across these two columns, and those are the transaction date and the local convenience store. Right? Local convenience. So mutate across the transaction date and the local convenience store. Want to make them want to convert them from numeric variable to a factor. So across transaction date and local convenience stores, we want to so we want to convert them to a factor. So yes, so that is how we would do it. So what we've done is we've taken the data, selected these columns, then we have modified the transaction date and the local convenience stores to a factor. So yeah, Carlotta, any comments? What are we doing next?
Yeah, so great job so far. We have the very last action for this question, which is pivot longer the data. And I think we can get inspiration from what we just did before, right? For question 2, if I remember correctly.
Yes, Carlotta. Yep, we can do that. Yeah. So yeah, just for proof, now these are factors, and factors in R mean, categorical. So now what do we want to pivot longer everything? Want to pivot longer everything except the price per unit. So price. So everything except all the columns except the price per unit to so the names of those columns. So the names too will be what will be features, right? Will be features, and their corresponding values too. We just lazily put them to values, and yeah, let's see how to get when we run that. So yes, so we have put the transaction date and the local convenience stores under one column known as features and their corresponding values under one column known as values. So with this, we can again test our answer, and yes, we have successfully put it in a form that will be easier for plotting. So Carlotta, we used scatter plots for numeric. So here we're going to be using box plots to see the categorical correlation or something. So we start again with the pivot longer data. We pass it on to ggplot. Then we make a box plot, or we specify want the x aesthetic to go to value and the y aesthetic to go to the price per unit. And then we want to color our box plot using the features. Again, we use the facet trap to apply these plots to those two distinctive features, those two distinctive values in our feature column. So again, we'll get two plots of two box plots. So we can see, let's say for the local convenience stores, we can see that that areas that have more convenience stores tend to have a higher distribution of price than those that have low or less number of local convenience stores. So this is a good idea, putting it into a categorical variable. So we are basically we're able to see the distribution, per price of houses that have areas that have more convenience stores. You can see that those that have more convenience stores tend to have a larger distribution of price, or a higher distribution of price than those that have less. So in terms of transaction date, we can see yeah, there's very not clear distinction, I would say, because really fluctuating between the dates, I would say, and probably it's because we of the encoding, like 2012.667. Probably if we had better encoding, we could split it into months or weeks and see whether we have a trend. But at this point, it's really difficult to determine the trend from the data with this type of encoding. So yes, I would suggest we take a price per unit and the others and move on. So yeah, but we'll see that in the next in the next question. So yeah, so that's how we started. We have looked at the relationship between the predictors and the outcome, and now we are at a better position to know what has a better signal and could be predicted and what does not. And yes, I think with this we are ready to start doing modeling. So Carlotta, please take it away. How are we doing next now?
Sure, sure. So thanks, Eric. From this data analysis we have done so far, we notice that, as you just mentioned, transaction date is probably the column which is less predictive, and maybe will require other preprocessing. But for sake of simplicity, we'll omit it for training our model, while the other columns are now potentially predictive, some of them as numeric features, some of them as categorical feature. So it's now time to get to the heart of the challenge and build our fast regression model. So to train a model, as we also said during the introductory presentation, we need to identify a training data set. So specify two subsets, a training data set and a test data set. So moving to question 4, what we are going to do is making a split specification of our data set state data, such that the 70% of the data set goes to training, while the rest goes to testing. So let's go ahead with solving our question 4, Eric.
Yes, Carlotta. Yeah, much pleasure. Let's see how we'll solve this. First step. So so we loaded the tidy model. So tidy model, uh, a set of packages that allow you to build machine learning models and doing modeling and statistical modeling in general and following good practices. So the first step is to randomly split the data into training and testing set. So we use the initial split function. So initial split allows you to create a splitting specification. So you're just saying, this is my data, and I want to get two, let's say two subset where the in our case we want to split by a proportion of 70%, so a proportion of 0.7. So you get a subset where one has 7% of the data and the rest has that percent of the data. So that's how you make a splitting specification. So yes, so that's part one of the question. You've made a splitting specification whereby you said, take specify that my data will be split into 70-30 each split. And once we have a splitting specification in Tidymodels, now the next step is to extract the test and the training, the test set and the training set. So the verb for extracting the training set is training. What I love about Tidymodels, Tidyverse in general, is the intuitiveness of this verb. So training is what will be used to extract the training set from the specification split. So Carlotta, I'm giving you a challenge. What do you think will be the verb that will be used to extract the testing set from the split?
Yes, so if it's easy as for training, I would say testing.
Yes, so
Make it
hold
right.
that thought there. Let's see whether we are right. So yeah, so let's run this, see whether we get some. Yes, so You're right, Carlotta. So yeah, the verb that extract the testing set from the splitting section is testing. So again, to recap, we created a splitting specification that that says, split the data into 70-30, 70-30 split specification, extract the training set using the training verb, extract testing set using testing verb, and then print out the number of rows in each. So we have 25 rows in the training set and 103 rows in testing set. So again, we can check whether our answer is correct, and boom, we are on track. So Carlotta, now we have our data. Is it time we move on to regression?
Sure, but first, I see a great question from the chat that I would like to answer to. So the question is from Kenneth. So I'm not quite sure about the use of set.seed. So which is the meaning of this function?
Perfect. That's a really good question. That's a really good question. So what set.seed allows you kind of so the splitting done by initial split is random. It will just pick 70 variables randomly with no replacement, and the rest will go to testing. So set the seed allows you to be consistent, such that when you yourself run these, you'll get the same data that we got when initial split randomly splits the data. So just ensures that when you share the data or when you share the code amongst your peers, you'll get random. The splitting that is done will be the same that you got. So it's a way of ensuring reproducibility and consistency of output. So if you'd change here, if we change to 2058 or 2022, we'll get we'll get a different split, different data in the training and tester. So yes, that's how set the seed does. Yep.
Great, thank you, Eric.
No
So
worries.
now we can move to question 5. So I think that there is another step that we want to use to prepare our data before training, right? So now we have our training data set, but there's another small pre-processing step, let's say, which include using a recipe. So a recipe in R is an object collecting a set of pre-processing steps to reformat the predictor values to make them easier for a model to use them effectively. So this may include, for example, transformations and encodings of the data to best represent their important characteristics. So the next question, question 5, is asking us to build this type of object, and a recipe object that we will call a state recipe, that will first remove the transaction date feature because we just discovered that it's not very predictive for our label price per unit. Then transform the local convenience stores feature into a categorical because we saw that there's no numerical correlation with the label, but there's some categorical kind of correlation with the label. And finally, center and scale, so normalize all the numeric predictors. So again, we have a quite complex question with 3 actions or 3 steps in this case of our recipe. So maybe it's worth to break it down into 3 pieces, right?
Yes, this is Carlotta. Very, very, very correct. Yeah. So yeah, let's go through it step by step. And yeah, let's check out what recipes are. Reminds me of a lot of baking, and which is a good thing. So yeah, so recipes, Carlotta said they allow us to do these pre-processing steps to our data. So we've seen during exported data analysis, we've seen that some category some columns may be well represented as categorical, and yeah, so some might require to remove. So this is what recipe allows you to do. Pre-process your data to make it ready for modeling. So, and the first step is to create a recipe. And simply creating a recipe, use the recipe function. So we instantiate a recipe and we give it some information. And we're saying price per unit, and then you have a tilde and a dot. So what this means is that we're saying, recipe, the price per unit will be the outcome, and everything else will be the predictors. So this is what this means. So we tell a recipe the roles of each column. So we are telling recipe the price per unit is the outcome, everything else is a predictor, and you can infer this from the data called state train. So that's what that's how we start with a recipe. So and yes, so once we have a recipe is once we've told a recipe the roles of the variables, now we move on to subsequent steps that actually do the pre-processing, and one of them is step remove. So as Carlotta said, we want to remove a particular column, and that is transaction date. So we've used the step remove function to remove the transaction date. So we want to remove the transaction date. Yeah, so Carlotta, now we have one step done, right? So moving on to the next step, which is step mutate. So once you've removed, so once we have a specification that removes the transaction date, we also want to specify the recipe to encode the local convenience stores as categorical, because that's what we saw. It's more predictive that way. So in exploit data analysis, we use the mutate verb. So to put this to a recipe, you'd use step mutate. So we are modifying the local convenience stores to categorical. So this would be step mutate the local convenience store is equals to a factor, which is categorical which means categorical in R. So a factor local convenience stores. Sorry. Yep. So this is a step that specifies, modify the local convenience store column to a categorical. And then the last one is to do normalization of numeric features. So Carlotta, I'll give you this. What do you think the step would be for doing this?
Sure. So we have we've just used step RM, so step remove to remove the transaction date column, step mutate to categorize the local convenience stores column. So of course we will need step underscore something, right?
Yes.
And since we want to normalize our numeric predictors, I would say that we need step underscore normalize.
Right, Carlotta. I will go with that too. Yes. So we want to normalize all the numeric features now. Yes. So yeah, step normalize would be it. So we've created a recipe, told it the roles. We've told the recipe you'll be removing the transaction date. So any data you get, remove the transaction date, modify the local convenience store to a categorical, and then normalize all numeric predictors. So that's what a recipe will be. It's a blueprint for pre-processing data. So perfect. And once you run that, you can get the what the recipe will be doing. So we can, yep, our answer is correct. So yeah, so now we have specified data processing bit of it. So Carlotta, yeah, so now we have a recipe that specify how our data will be put in a right form for a model. So time to create a model at this point, right? So yep, Carlotta, please take us to what we're going to be doing step 6.
Sure. So, as you just said, we have data preprocessing in order now. And the next step for question 6 will be make a model specification. And in this challenge, we'll try out a random forest model. Just to recall what random forest is, a random forest is a type of algorithm called ensemble algorithm, which works by combining multiple Bayes estimator to produce an optimal model. So these Bayes estimators, in the case of the random forest, are multiple decision tree models. So random forest applies an averaging function to multiple decision tree models for a better overall model. And question 6 asks us to create a random forest model specification, which we'll call RF underscore spec, which uses the random forest package as its engine. And then we need to set the mode to regression, because we could use a random forest, for example, also for doing classification type of task. But in this case, we want to build a regression model. So again, let's go ahead and answer to question 6.
Perfect, Carlotta. Yeah, very good explanation what random forest does. So we have a recipe again for preprocessing data. Now let's create a model specification. So in R, to create a model in R and Tidymodels in general, to create a model specification, you supply three things. One is the type of model you want. Here, you want a random forest, so you specify using a rand forest. Second thing you specify is the engine you want to use. So the engine is the R package that we used when fitting a random forest algorithm. And the third is the mode. Carlotta said is what either regression classification, because some of these models can do both. So let's get right into it. So the type of the model is random forest. So this is already filled in for us. So random forest, and then we want to specify the engine. So we want to set the engine so that our underlying R package will be the random forest package, just right here. So we want a random forest package, and just to finish up, we want to set the mode to regression. So setting the mode is regression. Just this easily, we have created a model specification that we'll be using. We want a random forest. We'll be using the engine to run forest. There are multiple engines to fit a random forest. Some will encounter them during the course, and then we want the mode to be regression. So that's how we make a model specific. Oh, that's how we make a model specification. It seems we do have an error. Yes, because the engine, it has to be random. I wrote rand forest, so that's on me. So random forest, is it? It is. I mean, yes, that's how we fix it. So the engine random forest the mode regression, and we can check our answer. And yes, the model specification is looking great. So just to recap, we have a recipe for preprocessing data. We have a model, we have a random forest model specification that will be used to act or fit the data that has been preprocessed. So we need something to combine the two. All right, Carlotta?
Yeah, exactly. And in R, what we can use is a workflow type of object. So a workflow is an object that first preprocesses the data and then both fit the model on the preprocessed data using the model specification and allow for potential post-processing activities. So in this way, with the workflow, we can bundle together the recipe we just built and the model specification. In question 7, that's what we will do. So building this workflow object using the recipe and the model specification we just defined.
All right. Yes, Scarlett. So let's bundle everything together, right? So we instantiate a workflow using workflow. So we are setting up the workflow, And then we want to add a recipe. So the recipe we created that will be preprocessing the data, we call it estate recipe. Yes, we call it estate recipe. And then we want to add the model specification that will be fitting the data, the preprocessed data. And then we do that by adding add model, and the model is random forest specification. So yes, and that's how we create a workflow. So this workflow has a recipe and a model. So that means every time it gets data, it will be one preprocessing the data in according to how we set the recipe. Once it preprocesses the data using the recipe, it will then be fitting the data using a random forest model that we've specified. So yeah, and now we can check whether our answers are correct, and all tests are passed. So yes, now that we have everything nicely in a workflow, we can then train the model by fitting the workflow using the fit function. So yes, so we time to train the random forest model. So again, we set seed for reproducibility, because the inner works now of random forest to pick columns in random and all that. So this ensures that we get almost the same results if we do it yourself. So to train a model, we take the workflow, which has a recipe. So first, it will first preprocess the data, and then fit it using the random forest model specification. So we fit it we fit our workflow using the fit method. And yes, we have, that was fast. 1 second. So we have, successfully trained a random forest algorithm. So we now have a fitted workflow. So Carlotta, would you mind, giving us a sense of direction now that we have fitted a workflow? What are we doing next now?
Sure. So we have trained our random forest model, and now we need to have some metrics, let's say, to understand how this model is performing. So if the model is performing any good, and we'll evaluate the model performance in this challenge based on two type of metrics: the root mean square error and the R squared metric. We already defined the root mean square error in the introdex as a measure of the differences between predicted and actual values, while the R-square statistic, also called coefficient of determination, is a relative metric in which the higher the value, the better the fit of the model. So this metric represents how much of the variance between predicted and actual label values the model can explain. And question 8 is asking us to calculate these evaluation metrics and generate, by building a metric set and then generate predictions for the test data set, in a way to validate our model.
Perfect, Carlotta. Yes, thanks for putting that into perspective. So the first step, now that we have a train model, is see how well it should perform on your data. So let's create some metrics to evaluate it. So we use the metric set. So as the name suggests, it creates a set of metrics, and these two metrics are the root mean squared error and the R squared. So that's how we create a metric set. So now that we have a metric set, so time to make predictions on the test data, and then later use the metric set to compare how close these predictions are to the actual observed test data or observations. So to make predictions, so to use the trained model to make predictions on the test data, we use this function called augment. I love you can use predict, but I love augment because of this reason, because it will give you the predictions and then bind them to your data. So you want to take the fitted workflow, random forest workflow fit, and then you want to augment the test set. So here, this means that to take the fitted workflow and then make predictions on the test set and save them to the variable name results, which you can see once we run this. So test set not found. So we called it estate test, right? That's on me, estate test. So sorry, that's a good thing about our errors. Really useful. So really useful there. So yes, so using augment, we have used the fitted workflow to that one pre-processed the test set and then made predictions on it, and bind those predictions to the test data. So augment does all that for you. So these are the predictions. You can eyeball through to see the differences, but that would be not really good. Yeah, we'll use the metric set to do that for us. So again, you can run the grader, and we see we have failed. Why? Carlotta, would you help me here? Why have we
Yeah, of
failed?
course. Yeah, of
Yeah.
course. So I think we just missed a small thing of the question, because the very last action, the question 8 asked us was to rename the predictions column, right? So we need to rename the predictions column with dot pred. The new name will be dot pred.
Okay. Let's see. So, sorry. Yeah. Here it was.
And
Bind
this
them.
is the good thing of having OTTR right in this challenge unit, because you also gain some tips on how you can go ahead and fix what you just failed.
Yes. So very helpful. So let's see. What do you want? So then rename the columns containing from .pred. So we want to rename from .pred to prediction. So that was so and then what we want to do is once you've made the predictions, want to rename the .pred to prediction. So to do that, we use again a verb that is very self-explanatory itself, and the verb is rename. So we want to rename, want to create a new name known as predictions, and predictions will be the old name. So we want to rename .pred to prediction. So the syntax for that is you supply the new name, which will be the old name .pred. And once you run that, we've successfully renamed .pred to predictions. A better verb, a better column name. So yes, now we have our column names correctly. Perfect. And the test are passed. So now that we've made predictions, now that we've made predictions on the test set, so what we'll be doing now is to see how well the model performed by comparing the two. So we had our metric set, and that's what we'll be doing now. We created a metric set called eval metrics. So to evaluate the model performance, the eval matrix takes data, which is the results that we've just created up here. We give it the truth. So the truth column is the price per unit, and the estimate are the predictions that we just made. So this will calculate the model performance on the root mean squared error and the R square. So you have a root mean squared error of 5.23. Not bad. We that means our predictions are off by around five price per unit, We have our R squared of 84%. So that means our model can explain 84% of variability in the data. So yeah, this are looking good, and we can go ahead with this. So again, we plot this is just a plot to based on what Carlotta explained earlier. So we want to make a plot of the predicted labels versus the actual labels, and then we make uh, a straight line through a regression line through the plot, so that we can measure how. Just give you know an example of, or a brief explanation how well the predicted values are far from the actual label. So yeah, that's just a plot to do that. And so we see that our model is pretty good. Has a low root mean squared error. It is less than 7. 7 was our target. We went below that. Has a root mean squared of 4%. And our variables, our predict variables, not that far from the actual variables. Now that we have this model, the next thing will be to save it, so that we don't have to run it over again, and then we can use it to, get 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 a prediction on new data that you've never seen out there in the world. So how do we save our model? So we started library here. So here just ensures that we are, in this environment where this notebook is, and then we save the model using save R RDS. So we save the fitted workflow, because it really it's of good performance, and we save it as we provide the name that we want to save it as, and that's rf underscore model.rps. Now that we've saved this model, we can use it for scoring or inferencing. So that is using it to predict for new data we want out there in the world. So for instance, let's say we have been given a new data set. These are we have been given a new data set which has these variables, and we've been told, what would be the approximate price for these houses based on these features. Now that we have a new data set, would be to load the model. So load the model using read RDS and the name that we save the model. Once we load the model, again, we can use augment to make predictions and bind them to the new data that we had. So that's it. Yeah, so we've saved the model, and we've gotten new data, and then we've loaded the model and used it to make predictions on new data. And so that's a typical workflow of doing regression. We started off by doing exported data analysis, just getting a feel of how the data relates to the outcome. And then we created a recipe that does the pre-processing, made a model specification, combined them in a workflow, fitted the workflow, evaluated the metrics, and so the model is a good one. And we used it to make new predictions on new data. So I think that was a good ride. And Carlotta, giving it back to you. Please. What is our call to action after all this?
Sure. Thank you, Eric. So while maybe we wait for some questions from the chat, or any kind of comments you want to share, I would like to wrap up the session. So we can say that we've gone through our goals for this session. We dealt with what is regression, when to use a regression model, how to train and evaluate regression models, how to experiment with different kind of models, and also we dealt with an hands-on challenge for creating a random forest model for a regression problem. Of course, we could not cover everything, but to learn more, you have the Learn module that include also this challenge we just go through today. So you can explore more and learn more on your own, and also maybe rerun this workshop on your own and how to grade yourself. And also remember that this is a series for our developers, students, beginner learners. So this is the second episode of the series. You can watch it on demand. Also the first episode. This episode as well will be available on demand. And the following, don't miss up the following episode that will be about classification models and how to create classification models using R and Tidymodels framework. So we have a good question from the chat. So I would like to know more about why we used random forest. So I would start answering. Then maybe Eric, you could add on that. I'm sure you will have some ideas on that. Tree-based model in general are very intuitive algorithms to start with, because they are step by step. They are quite intuitive, and they have a step-by-step approach of dealing with data. And random forest are ensemble algorithms which use tree models as a base estimator. And they are also one of the most common and most popular algorithms used for both regression and classification. So that's why in this challenge we chose random forest model.
Yeah, Carlotta. I think that was answered very well. There are some of this off-shelf model that can really work well on new data. They're really good at that. But yes, but that was our choice. We could have gone for boosted trees or something, or our SVM, support vector machine. But yeah, so we also leave it out to you there to try out other regression models, probably to some hyperparameters for the random forest that we did here, probably such as the number of trees or the random picked predictors, probably to improve performance. But it's also very open for you to try out different types of models and see what better fits the data. Yep. So that's what I would add on to that. Thanks for that good question. Thank you, Carlotta, for that brilliant answer.
Great. So thank you. We, of course, we encourage you to go ahead and try out experiment with other models. So we have a similar question, I think. So what determines the type of regression analysis to use?
What? Pardon, Carlotta. What determines?
The type of regression analysis to use.
Okay. So I haven't really gotten that question well, but I think the person meant what type of regression model to use, or
that's how I interpret the question as well.
Yeah. So yes. So I would say what determines that is mostly from the exploited data analysis part. For instance, if you see, for instance, if you see the data that has really distinctive features, between, has distinctive predictors, a simple model such as a linear model could really work, but to see if even though there aren't really very linear relationships between the predictors and the outcome, you may want to experiment with with further non-linear algorithms that can pick out these relationships between the data, and such as a random forest or a boosted trees or support vector machines. So I would say it's mostly tied in the first exploited data analysis, how your data is. That's why we really do not want to skip that part, because really brings an understanding of how the data and the next subsequent steps. So that's how I would answer that. But yes, and I'll add it by saying, as always, please, feel free to try out one or more models. And also, in some point, you can combine a linear model and a tree model. It's ADA, I would say, but also you as a practitioner always feel free to experiment with multiple models. Just that's how I would answer it. Probably, Carlotta, you have some other views. Yep.
No, I think I totally agree with you. So, as you just said, and we also mentioned it during the workshop, the first thing, the primary task of data science is data analysis and data visualization. So it all starts with that. This already can give us an idea of what type of model we can start to use. But of course, then we should experiment to see. I mean, we have evaluation metrics, right, to compare different kind of models and see what is performing better with respect to another. So we have in this with using evaluation metrics, we can have an objective type of comparison between models.
Yep. Yeah, that sounds good. And also we've covered it in one of the modules in the course. So please feel free to check that out. Also, yeah. But thanks for that question.
Great. So I think we have one more question from the chat. This is a good one. So, do R is more effective than Python?
That's a good question, Carlotta.
Yeah, that's a good discussion to start, probably. I would not say that there is one language more effective than another. So it's more probably about which one is more intuitive for us, which one we are more familiar to, and also, for example, R is very popular also not only within developers and data scientists, but also within academics, for example, focused on economics, mathematics, or business, etc. So, Eric, what do you think about this type of discussion, Python versus R?
Yeah. I would say it's actually an interesting one, and I think I would say one, it narrows down on one, what to feel you are more comfortable with, because at the end of the day, I've come to find out that they all they all do the same thing, right? For instance, this whole challenge notebook or this whole module is also implemented in Python. If you just Google, if you just search create machine learning models with Python. So it means, with other languages you can do you can do data science. So yeah, so I would say it's find the language you're most comfortable with, because both can do the same tasks. And we're also seeing in in real world is data scientists tend to use both. I would say, so leverage on the on the on the strengths of both. So, for instance, you can find in one chunk data scientists as this probably R for exploratory data analysis and making beautiful visualizations. I feel R is very strong there. Probably that next chunk done it use Python to do another thing. So it's I would say it's at this very point in age, it's more about not R versus Python, more of R and Python and Julia and many other more. Just yes, that's how I would say. They really do the same thing at the end of the day. Yeah, so it's I would say choose the really most comfortable with, and yeah, if need be, you can also easily switch between the two because they are really similar in some sense. So yes, that's how I would say. That's how I would say, in my opinion,
Great. I
humble
think we
humble
could
opinion.
go. Yeah, sorry. I think we could go ahead with this discussion forever,
Yeah, yeah.
right?
Okay, yes, true. But yeah.
Yeah. But so another one, is there other engine we can use for model specification?
God, that's a really great question, Yes, and very observative. Yes. So yes, there are multiple engines in R. There are multiple packages in R for fitting models. So yes, we can use the random forest. God, sorry. Yeah, so you can use the random forest engine. There's also the yeah, there's another one trying. There are multiple yeah, packages. Yeah, so yeah, I think if you go to the tidy models help page, yeah, you probably will share this in the link, but in the chat. But yes, there are multiple. Go to the tidy models help website, tidymodels.org. Yeah, you can find all the engines that go with a particular regression or classification challenge. So yes, there are multiple engines for this. Yeah.
Yeah, so there are multiple engine for every model. So
For
the
every
first
model.
thing,
Yes.
yeah, so first thing is know which model you need, and then yeah, there are multiple engine for each model. Great. So thanks for this question as well. So yeah, great questions today. Very very good discussion. Great. Um, I think it's time to wrap up, right? So
Yep.
it was a very good session, a very good workshop, and a very good discussion with within the chat. So thank you everyone for joining and for participating to this discussion with us. And yeah, see you at the next episode, right?
Yep. See you at the next episode. Always, it was such a pleasure. Thank you for tuning in, and yes, can't wait to see you soon. Yeah, take care, and bye.
Bye. Thank you. Thank you, everyone.